This is an overview of the Arduino Control Lab in Python and MATLAB. We're going to focus on Python today and just give an overview of some of the source code that's available. I also have a link here for MATLAB if you're interested in using that instead. So this lab enforces principles of dynamic modeling. First principles, for example, here's a finite element analysis for the heat transfer of this little device right here. So we have a heater and a temperature probe, and we're going to be adjusting the heater to control a temperature. Okay, so we have a control, a measurement, a set point for our temperature, and we also have our actuator, our heater. And so we have two of these here. The newer version of the Process Control Lab is for, in addition to single input, single output, it's also for multiple input, multiple output. And we're going to go through a couple different examples here. One is dynamic modeling. We're going to do first principles, empirical or machine learning. We also have estimation as well. This is kind of related to the empirical, but it might be also a hybrid of first principles and empirical, where we have parameters that we're trying to estimate inside our first principles model. We also do Kalman filter as well as moving horizon estimation, which is a more advanced topic. It's an optimization based topic. In the controllers, we're going to use three different types of controllers. One is just a simple on-off proportional integral derivative controller, and then we're also going to do a more advanced one, which is model predictive control. So once we have a model, okay, from something like regression, where we do some step tests on our heater, and then we observe the temperature response. Okay, so there's the temperature response right there. And I'll show you how to run some of these files. And we might have an initial guess from our model, and then use an optimizer to correct that and get a better model. So once we have a model, then we can apply that in a controller. And so let me go down here to some of the examples of the controller. Again, what we're doing is we're changing right here, we're changing this heater and then measuring a temperature. Okay, and this is kind of the zoomed in view, but we're only using one set of these for the single input, single output case. Okay, so here's the on-off control. So if it's less than a certain set point, okay, I'll just say that's my set point right there, then it's going to turn on. Okay, so this is when it's below set point, and this is when it's above the set point, the temperature set point. Okay, the heater is going to turn on or off. And this is similar to how it's done like in a building or a home, where the heating is just on-off control. Okay, so then we move to something like a PID controller. So if the heater can turn to not just on-off, but to specific values that are in between on-off, then we can use a PID controller. And so in this case, you see there's less oscillation once the PID controller reaches the set point in this region. But this could probably be tuned a little bit better to come up to the set point faster. Okay, so that's a remaining challenge for this one. And then we see model predictive control. So we're going to use either a first principles model or an empirical model to derive this model predictive controller. And so you can see that the heater saturates initially, and then as it gets closer, it backs off even before it's reached the new set point. And you can see it's just some slight overshoot there, but very good performance on the model predictive controller. I'm going to actually show that. We're going to run the model predictive controller and see if we can get some similar results, and we'll just explain what's going on with some of these files so you can run them yourself. So I'm going to go to the course website for this. This is on the PDC website for the Python, and then if you go to the dynamic optimization course, you can find some of the MATLAB files as well. Okay, Arduino with MATLAB. So there's the MATLAB version right here with some of the files and example problems. Okay, but we're going to go back to the Python one, and then if you just scroll down here, you'll see temperature control. So go ahead and select that. This is the temperature control lab. There's a schematic of how to build the Arduino and the breadboard connections. We have different versions of this. Here's kind of an earlier version where we've breadboarded it ourselves. And there's the exercise with some of the challenge problems there, a little bit of source code in Python. But if you want to get this package that I'm talking about today, go all the way down to solution files. And this is our version 2 of the lab right here with the 2 inputs and 2 outputs. And there's some of the additional things that we're going to be doing with the lab. So go ahead and go to GitHub. There's a link right there, and download on the right here. Go ahead and download as a zip file, or you can use your git command to retrieve it. I'm just going to save it to the desktop. Okay, and then close that. Make sure you extract it, unzip it first. Okay, so we have Arduino files. Now you can see all of those, for example, step test. You can come in here and run this. Okay, and this will run the step test. It'll connect to the Arduino and then start manipulating the heater and then observing the temperatures. So once we complete that, okay, so it's going to step test. I'm going to close this. But it's going to generate a data file for us. Okay, I'll enable editing there. So first column is going to be time. That's going to be our heater. And then the third column is our temperature in Kelvin. And you can find this, the raw data is going to be here in the XLS file. I'll go ahead and click open. Okay, it looks like it didn't save because I closed it before it was ready to write the files. Make sure you hit Control-C if you're done with the step test, and then it'll write into the output files area. But I have some example data there as well. Okay, so then you go on to regression once you have that step test complete. Here's a second order fit. I'm just going to open up that, and I have my data file in there. You can replace this right here with your data file. And then if I run it, then it's going to use an optimizer to minimize the sum of squared errors between the model and the measured values. So you can see the initial sum of squared errors objective there, and then it's going to go in and try to optimize some of the parameters of this second order model to try to achieve a best fit. Okay, so that'll come up in just a second as the optimizer is working on it. We also have ARX regression. If you'd like to do a, for multiple input, multiple output, we'll get to that later. But we can also use this to identify things like, state space models and others. So if I open up this empirical ID, I'll run this at the same time. And you can see, I selected the wrong thing there. Okay, run module. And so it's going to identify a model, this time with the APMonitor modeling language, and then you can see it run through with the IPOP solver, and then once it finishes, it brings up this this fit of the data. Now you can see it actually does quite well. You can see the red and the blue lines there, and they're actually very close. So that leads us to think that this model predictive controller is going to work very well. We can also take first order plus dead time. Okay, first order plus dead time, and that will help us get parameters that we can use to tune a PID controller. Okay, so here's my second order fit, and you can see it's very similar to the ARX regression as well. Okay, and you can see the parameters there, the KP, tau p, zeta, and theta p for the second order fit. The first order one is there as well. Okay, now that's more in the PID controller. You need a first order plus dead time model in order to regress IMC or ITAE tuning parameters. Here's the on-off control. This one is, as I mentioned before, it just turns the heater on or off if it's low or high. And the logic for that is very simple. This is probably the simplest controller. And so here is the controller right here. Okay, so if we're below 120 degrees Fahrenheit, we turn the heater to 150, and else we'll turn it to 0. Okay, let me go on to PID control. So this is the PID controller. And if I just edit this, we'll go down and you can see right here is the PID controller. So instead of the on-off, now we just have something that's a little bit more sophisticated, not too much though. And it will calculate the proportional, integral, and derivative pieces of the PID controller right there, and then it will, when you run it, it'll do PID control. So you need to change your PID parameters, your tuning parameters, right up here. I just used the KP, tau p, and theta p that I got from the regression, and then I generated some initial default KC, tau I, and tau d values, but those could be improved. And here are the results for the PID controller as I showed you before. So it does a fairly good job, not very much overshoot there, and but could potentially improve on the rise time. Okay, now let's go on to moving horizon estimation. So this one is with the first order model that we had before. It implements the, here's the moving horizon estimation model. And then we also have a second order one as well. Slightly more complicated, but not much more. Just has a few additional parameters like KP, tau p, or theta, zeta, and then we also have this steady state starting value for the initial condition. Okay, the one that I wanted to show you though was this number 6 model predictive controller, and it's actually going to be using the ARX model that we had identified before. This was automatically produced. The ARX model was automatically produced when we ran that regression, and so let's go to, let's close that. Let's go to here and just run it. Okay, so I'm going to run the main MPC, and what it's going to do is import the MPC module and then do MPC init. Okay, and this is desired temperature is going to be, first of all, 80 degrees Fahrenheit. Convert that to Kelvin and then just input that in as a set point high, set point low right here. Those are just the initial. Then we get into the main loop right here. And I'll just show you where the model predictive control starts. So we have this section right here. That's the model predictive controller. You can change it from automatic to manual mode right here if you want. It just goes into this region. So it just looks for set point changes right here, and we'll insert those if there is a set point change. And so I'll change at 3 minutes. 1 minute, or actually 1 second, I'll change to 120 degrees Fahrenheit, and then at 3 minutes I'll change to 100 degrees Fahrenheit, and then that converts it into Kelvin. And then you can see the set point is inserted into the application, and then we'll run the MPC. We take a measured temperature in Kelvin and return the heater value, and then that heater value gets written to the Arduino down here. Okay, so let's go ahead and run this one, and these were the results that I had before for that. You can see it had the change in set point right here. You can see it ramp up to that new set point, and then there's a change down in the set point. But let's run this for at least Let's see, I'm going to run this for at least 6 minutes. Okay, so there's the runtime right there, and then it'll pop up some web pages and other things that we can look at to view our solution. The first web page that's going to pop up is, okay, just hit refresh when it comes up. Okay, there it is. So what we want to do is look at our temperature. Okay, this one right down here. Okay, just go and select the trend there. Then it'll open up this web interface right here. Okay, and let me make this just a little bit smaller so we can see it. Okay, I'm going to actually take this into the Edge browser. It does a little bit better with the touch. So I'm just going to copy this link, and I'll close this one. But you can see it heating up right now. I want to go back to the plot. I'll select that plot, and then we'll see the model predictive controller running. We can see the model versus measured values. So the measured was a little bit low. It's started a little bit lower, and now it's heating up. There might be a little bit of overshoot here, but it looks like it's doing a fairly good job of controlling that. If I come down here, I can also see my manipulated variable. Okay, and there is my heater, and so you can see that the future prediction horizon is changing as there are disturbances or other things going on with this system, and it's trying to respond to those. So here it is right here. If you ever get this orange error right here, just go ahead and select the plot again. It just means that it was writing, it was trying to write the plot file as you were trying to access it, and it's just a little bug with the flash player there. Okay, so you can see that it's doing a fairly good job of controlling to the set point. The set point is the black, and you can see it kind of marching along there. And then after a few minutes, it's going to have a lower set point. Okay, and what will happen then is it's going to then drop the heater value and then try to try to get it to follow that set point instead. Okay, so let's just, okay, this is still running. You can see the voltage there. Okay, it's making fine adjustments just to try to keep it, at the set point. Okay, and you can see it kind of plotting real time there. I'm going to go back to here. You also have this Python screen that shows the 2 as well. Although the other one shows not just the current values, but also the future predicted horizon. So the web page will show you the horizon. This will just show you what happened, the measurements that are in Python, or the value that's returned from the model predictive controller. So you can see that the voltage is still fluctuating a little bit. You could probably reduce that fluctuation if you tuned it just a little bit more. But for a heater, that shouldn't be too much of a problem. Okay, so this is, it's now going down. Looks like we passed the 180 mark. Let's see this, see if we're going to be going, reselect that plot. And there you can see the set point down. Now we're asking it to follow that reference trajectory there, the black line, but it can't. And the model knows that as well. The controller knows that. It's trying to do its best to follow that downward trend in the temperature. And so we'll see it working here. The yellow is the measured value. The blue is the model predicted value that we got from our the regression. So you can see it does a fairly good job. There's still a little bit maybe at the beginning, but it looks like it's tracking fairly well throughout. Okay, so let me go back here and see if okay, so this is still coming along. I'm going to refresh that trend one more time. Sometimes the flash player is just a little bit slow on how it does this. Let's see if this thing is still going too. Okay, and it looks like our Python crashed. Okay, sometimes this happens just with the communication over the serial port. So it stopped, but you know, it has gone for me a couple times and been able to complete successfully. So anyway, that is the Arduino controller right there. It's MPC. It communicates to the Arduino through a serial port. So we're running Python on, not on the Arduino, but on our Windows or Linux PC, and then it communicates over a serial link to the Arduino device. Okay, so that's it for the this demonstration on model predictive control. I spent a little bit more time on that, but there's a lot of files here. You can also do the moving horizon estimation and model predictive control, and it'll implement both of these. You'll see in here, let me go ahead and just edit this. Here's the moving horizon estimation code right here, the initialization, and then the actual MHE code, and then the MPC code as well, just mpc.py. And so when an MPC controller runs, it takes the parameters in from the moving horizon estimation, inserts those as measurements, and also inputs the temperature as a measurement. It solves the MPC, and then it just checks to see if it was a good solution. If it was, then return the new value for the heater. If not, then print some diagnostics here and set the voltage to 0. So that's in case it fails. So it did shut down automatically for us, and you saw that when it had that error. Okay, so that is the tutorial. Let me go back to the web page. Just mention one other thing here. So this is the more advanced, these are some more advanced applications I included there at the bottom. The normal lab, though, takes you through these 4 steps: dynamic modeling, where you do a first principles or an empirical model. You generate the data, fit the model, okay, and then you do a PID controller. So this is more advanced down below. So down at the bottom, these are the more advanced topics. Some of the solution files to the ones above, but also some extra ones like the moving horizon estimation, ARX regression, and model predictive control.